All right, let's take a look at section 14.7, which covers maximums and minimums of multivariable functions. So there's just one learning objective for this section, to find maximums and minimums of functions with two variables. So by default, those two variables will be x and y, and we'll have a function that's z equals a function of x and y. So we're going to look to maximize or minimize the z value. And again, that's just the default setup that can change around if we want it to. But at least for starters, we'll stick with the default. So from the textbook, the definition of a local maximum and minimum is stated here before us. Ultimately, what it boils down to is that we have a local maximum if there is a single point that's bigger than all points around it. We're going to say, think about some disk that's near wherever our point is, and we have a local maximum if it has the largest z value in that section, in that disk. Conversely, the local minimum would be in that same disk, but we have a single point that's smaller than all other points around it. It doesn't matter how big or small that disk is, as long as we can find a disk or some disk where our point is the largest point or the smallest point around, we can say it's either a local maximum or a minimum, depending. The text also makes a distinction between a local maximum and a local maximum value. Local maximum versus local maximum value. And the difference between those two is that the local maximum is the point, so some coordinate with an x and a y point, whereas the local maximum value is that z value, and it's a scalar. Same thing with the local minimum versus local minimum value. The local minimum talks about a point, while the local minimum value talks about a scalar. Let's go ahead and label those two pieces here and here. Those are both scalars compared to the local maximum or local minimum. Those are points. So a small distinction, but an important one. So we'll go back to defining what a critical point is, and it'll be quite the same as the critical point definition that we had back from single variable calculus, or Calc 1. So we'll say that f has a local maximum or minimum at a point if the first order partial derivatives of f exist there, and the derivative in the x direction is equal to 0, and the derivative in the y direction is equal to 0. So to recap, if we have a critical point and the derivatives exist, then both derivatives must be equal to 0. Let's come back and rephrase that a bit, and also define a new point called a saddle point. So point AB is a critical point or a stationary point if both derivatives are 0, or if either of the two partial derivatives do not exist. So if I look at a partial x derivative or a partial y derivative and they don't exist, then we'll say that that point is a critical point, just like we did back in Calc 1, where we said a point is a critical point as long as the derivative is either 0 or does not exist. But we're going to take that a step further in multivariable calculus and say that a critical point that is not a maximum or a minimum must be a saddle point. And the diagram of a saddle point is pictured here to the right. That'd be that point there in the center. Let's pick maybe a different color that'll show up better. Red should be good. And it's called a saddle point because, well, it kind of looks like a horse's saddle. Where it's concave up if I look at it from one direction, but concave down if I look at it from another direction. So it looks here, if we're in the YZ plane, we appear to be concave up, but in the XZ direction, our graph is, or our shape is going to be concave down. So that'll be a saddle point because it's neither a maximum nor a minimum, but it is a critical point since it's right at the vertex of parabolas in a couple of directions. So we know that those derivatives should be 0 there. So that's a saddle point. And similarly to Calc 1, we'll have a second derivative test for Calc 3 as well. That says, suppose the second partial derivatives of f are continuous on some disk centered around whatever point we want to talk about. And we know that the first order partial derivatives, so the partial x and partial y, are both equal to 0, meaning that our point's a critical point. Then we're going to define this new thing that we call d, where we're going, it's a function of whatever point we want to look at. So it's d of a and b, and it's defined as the second x partial multiplied by the second y partial minus the, I guess the one of each partial. So the we're taking a partial derivative with x and y and squaring it. And we're going to use that value to tell us something about the point that we're interested in, about our critical point. So if we go back to what we looked at in Calc 1, the second partial derivative told us what the concavity of our graph would look like. And we said if we had a critical point in a spot that's concave up, that must be a local minimum. Since that would be at the bottom of some bowl, concave up, we'd have a bowl facing its normal direction. So we have a local minimum if it's concave up, versus if we're concave down, we would have had a local maximum. And we want to apply that idea to our multivariable calculus. But now, as we saw with a saddle point, it's going to be important that we're concave up or concave down in more than just one direction. So if we are going to have a local minimum, according to the second derivative test, we must be concave up in all directions. Just like if we're going to have a local maximum, we must be concave down in all directions. So the way that this is going to work is that if d comes out positive, then we're going to have either a local maximum or a local minimum. We'll get into how to tell that in a minute. But if d is negative, then that point is neither a local maximum nor a local minimum, which means it's going to end up being a saddle point. If this test comes out to 0, so if d is equal to 0, the test will be inconclusive, pretty similarly to the test that we had back in Calc 1. So let's talk about what these pieces mean. So if d comes out positive, and we look at the setup of how we calculate d, it's the 2 second partials multiplied together minus some other term squared. So if d is going to come out positive, that means that both the x second order partial and the y second order partial must have the same sign, because I need the product of fxx and fyy to be positive. That's only going to happen if they both have the same sign, which means if both the x second partial and the y second partial have the same sign, they're going to have the same concavity in both the x and the y directions, which is a good step toward trying to say that we have a local minimum or a local maximum, which is why, in order to come up with either a local minimum or a local maximum, we need d first to be positive. Then there's the second part of the test, which here says specifically that the x second order partial must be positive to have a local minimum or negative to have a local maximum. But really what it's saying is that since we know the x and y second order partials must have the same sign if d comes out positive, then we only really need to check one of those two partials to see what kind of concavity we have. Because if the second order x partial is positive, that means the second order y partial is positive as well. So if we're concave up in the x direction, we're also concave up in the y direction. So we must have a local minimum there if we are concave up in all directions. Conversely, if that second order x partial is negative, that means it's concave down in the x direction. Because d is positive, we must also be concave down in the y direction. And since we're concave down in all directions, is what this must mean. If d is positive, we must have a local maximum there. Since again, concave down in all directions. So by the text, it says specifically check the second x partial, but you could check the second y partial and get the same results. So it doesn't matter which partial we check here as long as we check one of them. All right, let's use that in an example. So finding all the critical points of the function f of x and y equals 3 plus xy minus x minus 2y. And we want to decide if we have local maximums, local minimums, or saddle points. So what we'll want to do first is look at the x partial. So that if we take a derivative with respect to x, we should get y minus 1. And we want that equal to 0, since we're going to need the x partial equal to 0. In order for that to happen, y must be equal to 1. We'll repeat the same process with the y partial derivative. And we should come up with x minus 2 equals 0. Must mean that x is 2. If we combine those two pieces together, since we need both the x and the y partials to be equal to 0, our critical point must be at 2, 1. So there's the first half of the problem. We know what our critical point is. Now we just have to classify it, which means we'll need to calculate our d value. So we'll come up with our second order x partial, which if we take the derivative of y minus 1 with respect to x, we're going to get 0. And if we look at the second order y partial, that's going to be the derivative of x minus 2 with respect to y. So that's also going to come out 0. And we'll come up with the mixed second order partial derivative. Either way, we should come up with 1. Either take the derivative of y minus 1 with respect to y, or the derivative of x minus 2 with respect to x, come up with 1. So d should be 0 times 0 minus 1 squared. So it comes out to negative 1. Which means that it doesn't matter what point we plug in, we're always going to get that d has a value of negative 1. Which must mean that because d of 2, 1 is equal to negative 1, that it is a saddle point, since d came out negative. We bring back the description up at the top of the page. If d is negative, then that critical point is not a local maximum or a minimum, which means it's a saddle point. All right. So now that we know how to find and classify critical points, our final goal in this section is going to be find the overall maximums and minimums on some closed and bounded set. So this will be similar to the extreme value theorem from Calc 1, where we just had the one variable, but now we'll have multiple variables. So we'll start off with a couple of rather wordy textbook definitions, where we define what a bounded set is. We say it's one that's contained in some disk. In other words, it's finite in an extent. Then in terms, it's closed and bounded set. We make the following counterpart of the extreme value theorem in 2 dimensions, which is the theorem listed here. If f is continuous on a closed bounded set in D, then f attains a an absolute maximum value and an absolute minimum value at some points in that region. So there's quite a bit to unpack there. So let's start by talking about what the important pieces are and what they mean. So we talked about a closed bounded set. And I think probably the best way to understand what that means is just look at some examples. So closed sets would be the two examples we have up here at the top. So it's a set that contains all of the points that are on its boundary, where a set that is not closed is any set that doesn't contain some point on its boundary, which is what we see in the second row, where we have a circle where none of the points of the boundary are included, which would mean it's not a closed set. Instead, it's an open set, or the circle where all of the points on the boundary are included except for one, the one up here at the top. But that one point is still enough to make it so that this is not a closed set. And we also have a square where only one of the four sides are included. So that would also not be a closed set. So what we're doing here is looking at the boundary of each set, boundary just being the edges of our sets. So when we're looking at the circle, the boundary is just the outer edge of the circle. When we're looking at the square, the boundary would be each of the four sides of the square. And those boundaries are going to be important because we must have a closed set, meaning a set that includes its own boundary in order to imply the extreme value theorem, which says as long as that we're continuous on this closed and bounded set, we can find an absolute maximum and an absolute minimum somewhere inside this set. So let's maybe try rewriting things in a way that is a bit simpler to understand. So definition of a boundary, we have a boundary point of a region D is a point near other points of D and points outside of D. So this purple line over here is the boundary of D. If we've got just some nebulous green set that's over there, and then there's this boundary edge that we've drawn in. Then what the theorem that we used from above, the extreme value theorem, what it's really saying is that all absolute maxes and mins must occur either at a critical point or at a critical value on the boundary. So if we're going to find the extreme values on this set, we have a three-step process that we'll take to do that. So first, we'll find all of the critical points that are in D. Then we'll find all of the critical points that are on the boundaries of D. And then we'll just check all of those points, and the largest point is the absolute maximum, and the smallest point is the absolute minimum. So let's put that into practice. Same example that we looked at from earlier, but this time we're going to find the absolute maximum minimum of that function on the region that's the closed triangle with the vertices 1, 0, 5, 0, and 1, 4, illustrated here. So we already found the critical point from earlier to be 2, 1. Since that was the first part of the example, and if we went to go plot 2, 1, it should be somewhere about here. So that critical point is included inside this region, so we'll go ahead and check its value when we get to the extreme value part. So for the rest of the problem, we need to check all the critical points on the boundary. So that means we need to get equations for each of these boundaries. We've got a line that's running from 1, 0 to 5, 0. That's just a horizontal line running along the lie value of 0. So it must be just y equals 0. Would be this bottom boundary line. We also have a vertical line running from 1, 0 to 1, 4. That's going to be the line x equals 1. And finally, we have a line running from 1, 4 down to 5, 0. That's a rise of -4 and a run of 4, so our slope is -1. So the equation of that line should be y equals -x plus 5. So we'll have these 3 boundaries to check. So let's go ahead and plug that stuff in. So I'll start by looking at, let's look at that bottom boundary, which would be the function f of x and 0. And so we'll just replace y with 0 to get the this shape, or this region along its bottom boundary. So this should be 3 plus 0 minus x minus 0. Or if we clean that up a bit, 3 minus x. Then we'll want to get a derivative here. This is now just a single variable problem. So the derivative along this boundary line should be -1. So we see that along that particular boundary, we have no more critical points. So we'll just need to check the endpoints of 1, 0 and 5, 0. Next, we'll check another boundary location. This time, we'll look at the left boundary where x is equal to 1, and plug everything in. So this will be 3 plus 1 times y minus 1 minus 2y. And if we simplify this a little bit, we are looking at 2 minus y. We'll take a derivative here as well. And we come up with -1 once again. So there are no critical points along the left boundary either. So finally, check that third boundary, where we'll have x and y, which was equal to 5 minus x. And we'll plug that in for y. So 3 plus x times 5 minus x minus x minus 2 times 5 minus x. And we'll clean up this equation a little bit as well and see what we come out to. So now we'll have a -x squared. So our x squared term. We gather up all of the x terms. We have plus 5x minus x and plus 2x. Altogether, I believe that's plus 6x. And then our constant terms, we will have 3 minus 10 is -7. Double check that math real quick. 5x minus x plus 2x. Yeah, that comes out to 6x. And once again, we'll get a derivative. This one should come out to be something a bit more interesting. We'll have minus 2x plus 6. Let's actually move that guy out of the way. Keep it consistent with the other ones that we did. And now, this is something that we will get an interesting result if we set equal to 0. In fact, we get x equals 3. So along this border line, we'll have an x value of 3, and if x is 3, then y should be 5 minus x, so 5 minus 3, which is 2. So we'll have the point 3, 2 that we'll want to compare as well. So if we come back up to what we had, we found another point at 3, 2, should be about right here. For the sake of clarity, let's change the critical point we found earlier to be red, just so it doesn't get confused with the blue lines that we've been working with. So, altogether, the points that we're going to want to check. We'll want f of 2, 1, which was the critical point we found initially. We'll want to check each of the vertices of our boundaries. So those were purple. 1, 0. We'll want to check f of 1, 4. And finally 5, 0. And we'll also want to get the point that we just found, which was at 3, 2. Yeah. So these are all of the critical points and critical values along the boundary. So the extreme value theorem tells us that if we compute these 5 points, the largest value will be the absolute maximum, and the smallest value will be the absolute minimum. So if we plug some stuff in, 3 plus xy, so this is 2 times 1, minus x, which is 2, minus 2y, which is 1, and see what we come out to here. So 3 plus 2 minus 2 minus 2, I believe, is 1. All right. Then we'll do the same thing for that boundary point. At 1, 0, we should have 3 plus 0 minus 1 minus 0, which is 2. So move these out so they're all in a line. At 1, 4, we should have 3 plus 4 minus 1 minus 8, which is 0. 5, 0, 3 plus 0 minus 5 minus 0 will be negative 2. And finally, 3 plus 6 minus 3 minus 4 comes out to 2 again. So if we go through and look at what we have, we were looking for an absolute maximum and an absolute minimum. And we should see that our absolute minimum is right here at 5, 0, because it has the smallest value. Absolute min. And our absolute maximum, we actually have 2 of. Here and here, assuming that my math came out correct. since both of those 2 points had a value of 2. So we have 2 absolute maximums. One at 1, 0, and the other at 3, 2.